Good morning, everyone. I'm Melanie Frappier. I'm a colleague of Steve here in the History of Science and Technology program. And it's my pleasure to introduce Chris Smeenk to the Newton workshop. Chris, you all know, is from the Development Institute of Philosophy / Department of Philosophy at the University of Western Ontario, which produces the greatest graduate, I think, don't you think? Chris has been working on the scientific method and justifications and knowledge of physical theories for quite a long time now. And he has worked on everything from the simple pendulum to the time machines. Don't bet against him on time machine. He's going to win. And of course, as a graduate from the HPS program in Pittsburgh, he does history, he does philosophy, but most importantly, right, the focus is on science as it is practice. And today he's going to tell us about cosmology and physical astronomy in the Scholium. Welcome, Chris.
Thank you. Well, thank you very much, Melanie, and thanks to Steve and Stefan and Scott for organizing such a terrific symposium. And it's a special pleasure for me to be speaking with Ted McGuire here, and another chance for us to talk about Newton. The place where I really discovered a love of Newton was in Ted's seminar many years ago, so it's a pleasure to be back in his company.
I remember well.
So. So, in one sense, the era from the publication of Descartes' Principia Philosophiae in 1644 to the middle of the 18th century could be thought of as a century in which the work on the hypothesis of vortices was something that was quite central to mathematical physics and astronomy. And so, if you wrote a list of people who had studied vortices as an explanation of either planetary motion or of terrestrial gravity, that list would include many of the greats of the era. Leibniz, Huygens, of course, in the late 1680s in response to Newton. Euler, a variety of people in the 18th century that I haven't listed. In some sense, it was a very active era of research on vortices. But of course, in the middle of this era, we have a very strong argument against vortices by Isaac Newton. And so this, in the central, as Andrew mentioned last night, there's a sense in which Newton is quite at odds with his contemporaries in his assessment of vortices as an explanation of planetary motions. And so the very first paragraph of the General Scholium, which I have to admit I'm in a luckier situation than most of you, this is probably the most straightforward paragraph in the General Scholium in terms of just understanding the text. Actually, the first two paragraphs. Newton presents three arguments against the vortical theories. The first is that the motions of the planets are incompatible with the approximately Keplerian motion of the planets is incompatible with the motion of an object that would be embedded in a vortex. So this is something that he developed at length in Book 2. I'll come back to that briefly, but he gave a quantitative account of vortices as opposed to one thing I meant to emphasize here. Descartes' arguments are very qualitative in his description of a vortex theory. It wasn't a priority for him to give a quantitative description of the motion of bodies that would be produced by their being carried around in a vortex. Newton, on the other hand, was interested in giving that quantitative account. And the opening argument, the opening two lines of the General Scholium, he refers back to this claim that the Keplerian motion of the planets is incompatible with the motion of objects embedded in a vortex. He also emphasizes that comets will be very difficult to reconcile with vortical motions because they are in effect zipping about from all directions through the solar system, and it's hard to imagine them as being carried around in some common vortex that's carrying all the planets. As you all know, the planets all move in the same direction, and so it's easy to imagine them as being carried in one common vortex. But given the speed and the angle at which the comets are going through the solar system and going through the orbits of the planets, it was hard to imagine how these could be carried through the same vortex. And finally, again, this is just the brief summary that Newton gives at the outset of the general Scholium. He says, all bodies move very freely in the celestial spaces, and therefore planets and comets must revolve continually in orbits given in kind and position according to the laws set forth above. So he's referring here to the question of whether you could see any detectable resistance that the objects feel as they move through a vortex. And he's arguing that you can't actually see any such resistance in the motion of the planets. Now, what I want to say today is mainly an effort to put those comments in context. So one surprising thing is that these are arguments that occurred to Newton in the early 1680s as he was working on the Principia. He's recapped his own reasons for rejecting vortical motion. In the period when he was still in many ways a Cartesian and was abandoning the Cartesian picture and leading to the picture they developed in the Principia. So I'll say something about the pre-Principia vortex theories and Newton's rejection of that. Then I'll say something about his response to the developments after the Principia. Secondly, I think in the general Scholium, it's important to recognize that because of the responses of Leibniz and Huygens, who in effect did what Descartes never had done in developing a quantitative vortex theory, Newton's response, although it was much delayed, was to shift the terms of the debate to a more methodological debate against the vortex theory, in which he was attacking one of the main things that the vortex theory advocates emphasized, namely the explanatory advantages that their view supposedly had. And so I see the general Scholium as part of recasting the debate with the vortex theory, not as a straightforwardly empirically debate, as perhaps it was in the earlier iteration where he was responding to Descartes, who just clearly did not have a successful account. And in the later debate, he's both arguing against the vortex theory and presenting the Principia as offering an alternative program for natural philosophy. And in the final part, which I'm not sure how much time I'll have to devote to this, I want to turn to a set of questions that actually arise quite naturally if you consider the kinds of things that were relevant to the questions of vortex motion. Namely, what's the effect of all these comets zipping through the solar system with all kinds of different angles of inclination? How is it that you could maintain a stable solar system with that sort of constant interaction with comets? And how could this solar system have arisen to begin with? So these are questions that came up most forcefully for Newton, of course, in his correspondence with Bentley. I'm going to say something briefly about those as well. Okay, so all of you know certain texts which characterize Newton's work in the early 1680s as he's abandoning the Cartesian context. I wanted to present you with a text that you probably haven't focused on as much in thinking about how Newton compares with Descartes. So this is a text that Jim Ruffner has discussed recently and translated. It's a text describing comets. And here I've selected a few. There's about 15 propositions on comets that are listed on this holograph manuscript. We know it's between 1681 and 1684 because there's a discussion of the comet of 1680, which Newton did observations of. And it's clearly prior to the de motu drafts. So this was written at a period where Newton was actively considering a lot of questions as reflected in De Gravitatione and other manuscripts that you're perhaps, well, assuredly more familiar with. What I want to emphasize here is that there's this weird mongrel of positions, a weird combination of ideas that Newton is playing with as he's trying to figure out how to describe the motion of comets. So, for example, his second proposition is that the matter of the heavens is fluid. So he's clearly still working within a Cartesian context where he's imagining there being a fluid matter filling the heavens. And as he says, the matter of the heavens revolves around the center of the cosmic system in the direction of the courses of the planets. So he's giving a description of a vortex theory. But he's also got some other ideas that are being introduced, namely the idea that there's gravitation towards the centers of the sun in each of the planets, and that toward the center of the sun, and that the gravitation, that is, toward the center of the sun is far greater. So here, rather than one single gravity, he's imagining gravitation directed towards the centers of each of the bodies in the solar system. And he also discusses the possibility that the comet, the motion is accelerated as it approaches the sun and then is retarded as it moves away. So the thing I want to emphasize with this document is how much of a mixture of ideas Newton is playing with at this time and the kinds of questions he's pursuing, and at this point still trying to find his way through, are questions about the understanding of the motion of comets in a Cartesian context. How could you describe the motion of the comets given these first two propositions, that there's a fluid filling the space and that it's moving in a certain way? So there's some challenges here. Again, there's a number of manuscripts during this period. The one that I just emphasized is focusing on the question of how do comets move? Are they compatible with a vortex? Can you actually think of that description of the comets accelerating as they move towards the sun and then being retarded away? The sort of internal problem that Newton is dealing with in the manuscript is that, are these first propositions numbers 2 and 3 actually compatible with the idea in proposition number 7? How could you have the acceleration of the comet described that way given these ideas about the vortex? So that's the sort of problem he's struggling with in trying to decide how comets move and whether they're compatible with vortex motion. There are other challenges, of course. So there's the famous correspondence with Hooke in 1679 to 1680, where Newton is pushed to consider planetary motion as a combination of a tangentially directed motion plus something pulling the planets away from that straight line motion. And there's then questions that he's posing at this during this fruitful and difficult time about whether the planetary vortex could be compatible not just with the motion of comets, but with the motion of the planets as well. And it's during this period that he's first encountering the astronomical literature and beginning to understand the Keplerian features of the observed planetary motions and seeing whether they can actually be reconciled with the idea of a vortex. And there's another issue. This is one that Svi Biener and I have written on, and this is actually a paper that grew out of the seminar we took with Ted, although it had a long gestation period. And this is questions relating to resistance and how you could actually try to detect resistance to the ether. And so Newton was very careful to contrast ether resistance to other types of resistance like air resistance, and designed, well, first of all, had to understand pendulums well enough to use those as experimental devices to probe resistance in a way that you could then try to detect ether resistance. Now, of course, then starting in 1684, we have the series of de motu drafts in which Newton has emerged from this period of challenging questions with quite an achievement. Namely, he's able to, in effect, unify a sort of Galilean Huygensian treatment of accelerated motion with an understanding of physical astronomy derived from Kepler. So we have a Keplerian orbit understood now in the de motu drafts as a consequence of a particular kind of force. So in extending the Galilean Huygensian tradition, Newton introduces a particular concept of force that you're all familiar with. He then recognizes that Keplerian motion is going to be a consequence of motion under a central force. So this is, as I'm sure, again, you probably all know this, one of the interesting things as well about the series of the de motu drafts is the changing nature of the importance of resistance in understanding the claims involved with the planets. So initially, the project is to understand motion in resisting media, and that emphasis drops out in the series of drafts. So another thing that, so just to emphasize then briefly, what emerges from this period of the challenging questions I've characterized is first a quantitative account of planetary motion that treats it as a consequence of a particular force. And there's also then a quantitative treatment of cometary orbits, which is the culmination of the line of work that I described in that earlier manuscript. And this is something that Newton ultimately delayed the publication of the Principia for. This was a very challenging question to try to determine the orbit of a comet, given the conception of the comets as also being governed by the same force that governs the motion of planets. How can you determine the orbit that a comet, such as in this case, the example he used in the Principia was the comet of 1680 and 1681. How can you use the observations to fix this parabolic orbit with the sun at one foci? This was something that was quite challenging, but this would have been quite striking to Newton's contemporaries. This was in the first edition, a fold-out diagram, a figure showing this orbit that he'd been able to compute. And a few things that are particularly important about this is that this goes very close to the sun. It penetrates through below the orbit of Mercury, obviously. And so we have an example of then a highly eccentric orbit that follows the same rules as the planetary orbits, but crosses over all of the different planetary orbits that would have been governed by a vortex. So this would be shooting through the vortex. Now, as a result of these developments, we then have a kind of argument against the Cartesian vortex. The first is just that the simple inverse square force law leads to quam proxime, approximately Keplerian orbits. And a vortex, Newton develops this argument in quite a bit of detail in the end of book 2. A vortex, on the other hand, does not lead to approximately Keplerian orbits. And there's also a separate line of argument then that there is no ether resistance. This is again developed based on pendulum experiments, first conducted in the early 1680s, and then those experiments are reported in quite a bit more detail in book 2 of the published Principia. So it's impossible to detect ether resistance in pendulum experiments, and given that the inverse square law itself is sufficient to account for the motion of the planets, there's no sign of an additional resisting force that would be present on Newton's conception if there were an ether that the planets were moving through. So in the case of the celestial bodies, the argument is rather that there isn't any indication of departures from an inverse square force that would result from the kind of hindrance you'd expect an ether to produce. Now, in response to this was actually a quite ineffective argument against vortices for Newton's contemporaries. Rather than abandoning vortex theories, the response of Leibniz and Huygens and others was to develop much more sophisticated vortex theories that had quantitatively quite a bit richer descriptions than that provided by Descartes, and actually were much more mathematically sophisticated. So, and in addition to arguing that they could produce quantitative vortex theories that did much better than Descartes. So I see it as, in effect, Newton presenting the first quantitative vortex theory on Descartes' behalf. It was a very bad one, and he argued against it. But in effect, then the next generation of Cartesians who were mathematically inclined presented a new set of vortex theories that was not subject to the same objections. And in addition, they emphasized the explanatory value of vortices as mechanical hypotheses, as giving you an account of gravity that would rely on action by contact. So let me say a little bit more about these arguments. So the arguments at the end of book 2 in section 9 you can think of as arguments given a hypothetical, namely if the fluid vortex has certain features. I'm not going to go into those in detail now. They're on the 22-page handout with all the proofs. Sorry, that was a joke. Which you'll get later, yes. So the fluid vortex that Newton criticizes is hypothetical. He has to propose various features of it in order to argue that the motion in such a vortex would not be approximately Keplerian. But there's one option, which is always just we'll reject those features that Newton presupposed in developing that vortex theory. And it turned out there's a much deeper objection to the whole argumentative style of this section, which Johann Bernoulli made in the 1730s, and then other people later as well, which I can go into this in questions if you like, but there's an incorrect use of torque in the way he's describing these sort of rotating shells of matter. And this is actually a quite apt criticism. In addition, the argument against resistance, well, there were really deep problems with the Newtonian account of fluids and how the fluids would produce resistance. And in particular, in the fifth letter in the Leibniz-Clark correspondence, Leibniz indicates that he thinks there are different ways of understanding resistance that won't lead to this kind of problem of a failure to detect resistance through the ether. So these arguments that Newton gave against the ether were actually quite ineffective. And so I think there's a more detailed story here about Newton's interactions with Leibniz, for example, in the 1690s. And the immediate response to the proposal of alternative accounts of celestial motion and the Tintamen and other things. But let me shift now to the reframing of the project of the Principia in the second edition, where Newton really takes up these questions in the general Scholium and tries to argue more successfully against the vortex theory. So we all know that's a short list of additions to the second edition. But I think there's one sense in which you can see these additions, especially to the rules, to the general Scholium, the first two paragraphs as well as the fifth paragraph, as highlighting a methodological contrast. And here the target is shifted from Descartes to Leibniz. It's clear that the Leibnizian program is the one that Newton is contrasting his position with. And I think rather than only emphasizing the negative case against the vortical motion, you can see Newton is also emphasizing the sufficiency of gravity to account for all observed motions in the solar system and its ability to account for new things as well. I think he perhaps should have put more emphasis on the ability to extend to new problems, but in some sense, at this stage, he couldn't successfully make an empirical case that the Principia's possible ways of extending to these new problems had already been fulfilled. And what I want to emphasize now is that the Newtonian program, in a sense, wasn't fulfilled in any way in 1712 or 1713. It wasn't until 1750 where this program had been shown to be really fruitful. So what I mean by the Newtonian program in this context, I don't mean to be introducing a new term. It just means that we treat all the solar system bodies as the solar system motions as produced by the single force of gravity. And then if you look at the text in Book 3 following the argument of universal gravitation, you can see that what Newton is doing in Book 3 is systematically applying gravity to a variety of other issues. Once you've established universal gravity in Proposition 7, then he considers, in effect, the three-body problem, how to treat the Earth-Moon-Sun system, as well as other three-body issues where you're talking about perturbations of one body on the sort of simple two-body motion you'd expect. That includes, in the case of the Earth-Moon system, an account of tides, precession of equinoxes. He's interested about the great inequality, the effect of Jupiter and Saturn. Again, that's a three-body problem. And he's also then develops the account of comets at the end of Book 3. Now, one thing that's clear is that although this is very promising, and sometimes Newton overstates the case quite dramatically in saying that he's given a sufficient account of all these, even by the second edition, it's clear subsequently that Newton's treatments of these issues, although he's right to think that it's promising to treat them as all, in effect, problems within gravitation, treating them all as gravitational interactions among a certain number of bodies, his treatment is inadequate, mainly because of the mathematical limitations of the approach he was adopting. And they, in effect, set the agenda for celestial dynamics in the middle of the 18th century as people developed new mathematical tools to really tackle these problems. So, so in that sense, there's part of the Newtonian program which really, oh my, I'm using much more time than I expected. So, sorry, let me come back to one aspect of this program that's partly because Coates puts a great emphasis on comets, and this is again something that Newton mentions in the general Scholium. The diversity and regularity of cometary motion was something that would be very difficult for a vortex theory to capture, even the more sophisticated accounts due to Leibniz and others. And so Coates' preface in particular beats this drum very loudly, that the comets will be a challenge for Newton. Now I want to emphasize that there's, with the return of Halley's Comet in 1758 and 9, there was actually a quite important test of Newton's theory. That's not surprising, but the thing that I want to emphasize here is that in Clairaut's treatment of the motion of the comet, he actually had to include the effect of Jupiter and Saturn on the comet's motion in order to determine when it should reach perihelion. And so in that sense, at this point, we have a really clear test of whether universal gravity, which includes the interaction between Jupiter and Saturn and the comet as an important cause of its motion, gives an accurate description. Clairaut had to, it took an enormous amount of work for Clairaut to do this calculation. And more generally, there's another aspect of an analytic treatment of three-body problem. And this is where I said that the hypothesis of vortices sort of was thriving until roughly the 1750s. So this is where Euler, writing to Clairaut about an earlier problem relating to the lunar motion, which is again a problem that Clairaut was able to solve using mathematical techniques that were unavailable to Newton, in which Euler is really saying that this is finally a firm and well-established reason to accept the law of attraction, the law of gravity. Euler, of course, had been a fan and a proponent of vortices up until roughly this point. So in terms of the Newtonian program and its evolution in the 18th century, it's in the 1750s that research effort in vortex theories really drops out, partly given the successful treatments of problems in the successful treatment of the three-body problem, and this is an important extension of what Newton was able to do. Okay, so let me say something very briefly then about questions of origins of the solar system. So one thing that is important to keep in mind is that Newton had no way of constraining the mass of comets. So he had no way of knowing how the mass of the comets compared to the mass of the planets. And as I've just said, understanding the motion of Halley's comet required taking the perturbative effects of Jupiter and Saturn into account. If you imagine now the motions of the solar system, which are regularly being interrupted with comets zipping in on these highly eccentric orbits, if you think those are incredibly massive objects, then you would have an expectation that they could really perturb the motions of the solar system. Right? And there's no way of knowing how massive the comets were at this time. So I think these considerations then really pose an issue. How is it that we have a stable solar system? How is it that these comets zipping in do not perturb the motion of the planets considerably? And in addition, how did the solar system arise? So I think once you've abandoned the vortex theory and shifted to universal gravity, I think these are very pressing questions. And they were questions that Bentley in particular pushed Newton on in 1692 and 1693. And perhaps I'll say just very briefly, and this is where Newton first clearly formulates a design argument in response to these issues, that he doesn't think his account of gravity is sufficient to explain either the origin or the stability of the solar system. Here we have to have the intervention of some wise counsel to have arranged the system appropriately. So let me skip the second thing I was going to mention. I was going to say that there's another issue that Bentley poses, which is in effect, how do you apply gravity to an infinite uniform distribution of matter? I think this is a missed opportunity, but it will remain so. So let me then just come to the conclusion. So I've given a very brief overview of the development of ether theories, both in Newton's pre-Principia thought and much more sketchily in the general Scholium and then subsequent developments. And again, I think we can see Newton's initial arguments against a Cartesian theory as shifting the burden of proof to defenders. But some of these arguments were quite inconclusive. They relied on specific conceptions of how vortex theory would work and of resistance. Comets provide a much stronger case against the early vortex theory. But I think, and this is something that I might not have emphasized as strongly as I intended to, but the prospects for extending a vortex theory and a law of gravity as revealed in later 18th century developments are quite striking. So Leibniz's Tintamen, there's no way in which it can deal with interactions among solar system bodies in the way that Newton's theory does, and it doesn't have the same prospects for a more refined description of planetary motions that takes into account perturbative effects. And I think the empirical case in favor of universal gravity, really based on celestial dynamics, didn't become substantially stronger within Newton's lifetime. It was only much later that you could make the case that Newton's gravity gave you a much more successful description of solar system motions than competitors. And finally, I think I just want to close by emphasizing that given this picture, then the question of the origins and stability of the solar system is quite a pressing one, and this is where Newton argues in favor of design as the way of resolving this issue. Okay, thank you. Ted.
I see you did learn something in that seminar.
Oh.
All questions have to be.
But I would walk, I fall down the stairs.
He's exempt. Okay.
I think he's exempt, yes.
I'll try.
Oh.
Oh, thank you very much. There's something I'd like to mention. I'm sorry I have had a headache cold. The question of the cosmic stability in third book Principia. As you well know, the comet's tails play a great role here as a recruiter of motion, because the idea is that built into the system is the possibility that it will run down. Unless these motions and interactions are recruited. So I think that he spends quite some time, as you know, speaking about the comet's tail in the third book. I think it's a very important part of this whole cosmological picture. When you present it out.
Yeah, no, I agree. I don't have anything I think in particular to add, but that's certainly an important part of the picture, and he's very concerned about giving an account of the comet's tail, and seeing how that.
It's interesting that essentially it's an alchemical hypothesis.
Right. No, there's a lot of interesting work he does on comets, including that. So that's right. That's important.
Okay, the other people have to walk to the mic, and then the first one there gets to speak first. It's a race.
You can't walk, you can't talk.
I don't make the rule.
Well, now you've intimidated them, and they're not racing because Andrew doesn't want to show how slow.
It's a Canadian thing.
Come on, Karen.
Yeah, I can. It's just good for your body. You walk around, that's good to take your back.
Can we just hand this around? No, it's the only one we got.
It feels very to go forth.
It's another technical. Okay.
Thank you. That was great. One tiny point, and one question. So, tiny point is, I thought you said Leibniz was giving, along with Huygens, a more sophisticated, mathematically sophisticated vortex
Huygens
theory.
Wasn't giving a planetary vortex theory. He was giving one for the gravity near the surface of the Earth.
Yeah. But I thought you said that they were giving a more sophisticated Cartesian theory.
Oh, well, Cartesian in the sense just of being a
having
vortex.
a vortex. Okay, good, yeah. Because you wouldn't want to call Leibniz a Cartesian normally from most.
No, that's...
Yeah. But I think that's an outstanding point about the Tenderman, that it's a much more sophisticated treatment. And of course, you're absolutely right about the principles. Descartes does not have anything like that kind of sophistication, which of course is always a puzzle about why didn't Descartes develop, given his skills.
Also, it's not clear that he wanted to give
it's
not clear that he thought that there would be stable regularities in planetary motions that you would want to be able to give a precise description of.
Yeah.
Because the vortices would be interacting. The image I had was his explanation of a comet, which would be a sort of traveler from one vortex to another, and the vortices would be interacting with each other. And so within his system, it's not actually clear that you'd expect long-term stable regularities like Keplerian orbits.
Yeah, that's interesting. Yeah. Question about Euler. So this might not be fair because but I was just struck. So 1748, Euler publishes Réflexions sur l'espace et le temps, which is really influential for later philosophical treatments of space-time and motion, especially, of course, for Kant and others. Is there any, I just can't remember, is there any sense in which that text still has an important role for vortices in the way he articulates the priority of mechanics over metaphysics, because it's a really interesting case where if you're working in the Cartesian, in your sense, very broad Cartesian tradition, you might think we have to have vortices if we're going to have a sort of metaphysically intelligible account of the causes of changes of states of motion in the planetary system, if you see what I mean.
Right.
But I just can't remember whether Euler refers to them or not. And
yeah, no, I would be going out on a limb because my memory of Euler is not sharp enough to answer that. But I should look at that and get back to you. Yeah, so that's a very good question. Yeah, because there's the sense in which the empirical prospects for the vortex theory dim quite a bit with the success of the more sophisticated treatments of the three-body problem and so on. But the metaphysical motivation, or the sort of explanatory motivation, it's not clear whether that just sort of becomes less emphasized or whether it's something that people will actually be second-guessing, like was Euler. Oh yeah, the shape of the Earth. Yeah, no. Yeah. Yeah, no, yeah, of course, I forgot to mention that. That's another important consequence of universal gravity that Huygens had recognized, and that there was, so that's why I said it's, in terms of celestial dynamics, it's not until after 1739 that you really have new evidence from the solar system, but the shape of the Earth would have been, yeah, about a decade before that. So thanks for the, yeah, I'll look at the Euler more carefully.
We can make a little dance here. Thank you for an extremely interesting presentation. I just want to add a few points and have one question. One of the points is that in this more sophisticated, as you said, vortex theory, call it Cartesian in general, not in the specific sense that was pointed out by Andrew. There, of course, is also the whole discussion about what matter and material interaction is. And you see in the late manuscripts of Huygens and in the correspondence between Huygens and Leibniz that this becomes a very important topic. You find traces of this back in the general Scholium. So here, of course, the metaphysical discussion touches the physical or mathematical discussion. What kind of material ether is there if this ether is not have to have the properties of the ponderable media so that it causes not resistance? I think this is something which a bit lacks in your presentation, although it would not change anything to the general line.
Yeah, that's exactly right. And so there's one point in which I said the arguments based on resistance were weak, and this is one reason why they're weak, because you could have a type of matter which doesn't offer resistance. And in fact, D'Alembert showed that under Newton's own assumptions, this was much later in I want to say 1752, although I'm not sure, maybe Nicolo can correct me if that's, there's actually, given the assumptions, Newton's own assumptions about the type of fluid he was describing, there would be no resistance to any body moving through that kind of fluid. So I think the question of resistance is puzzling both on the metaphysical side of what types of matter are you pondering? Are you thinking of immaterial ethers that don't offer any resistance? And also on the technical side of how is it? What are the mechanisms by which a fluid offers resistance to bodies moving through it? And how should we describe that? And it turns out that Newton's way of describing it in Book 2 was deeply flawed. So his account of resistance there doesn't actually support his claims about the planets would have to feel some hindrance moving through a celestial ether.
Yes, and of course the general Scholium is a key text to understanding his own puzzlement with this metaphysical aspect of the question.
Yes, yes.
A second little point is, I was very interested in what you said about Euler and Clairaut, etc., this 18th century Nachleben of this whole debate. The interesting thing is, even after Euler leaves the vortices idea behind because of this argument, which we established very well. Of course, and this is quite interesting, I think, the technical part of the whole D'Alembert, Euler, Lagrange approach, the analytical mechanic approach, strongly remains tied to this implicit metaphysics of vortices, with the least resistance principle, with the virtual work principle, etc., etc., etc. It is historically clear, I don't say this is a logical necessity, but it is historically clear that this technical apparatus was developed in an environment where This was the metaphysical background idea. And it is quite interesting, I think, that the technical apparatus of physics remains up to, say, early 20th century strongly determined by this.
That's very interesting. So I'd want to get a clearer sense from you in what sense the vortex theory in particular was leading to the sort of calculus of variations and minimization ideas that you mentioned, because I think so it's certainly the case that there are different lines of thought within rational mechanics, and I think people often tend to overemphasize Newton and neglect the important traditions that were coexisting, in which treatments of torque and angular momentum and extended bodies were much more, were dealt with much more successfully, and then were integrated into the work of Euler and others by mid-century. So it's partly there's a confluence of, so Newton in effect is doing point body descriptions of interacting systems. And Leibniz and others, even when even at the same time as Newton was developing this, were really looking at fluids and extended bodies as an appropriate starting point for mechanics. And so you can see the later work in the 18th century, it's incorrect to say that it's sort of purely Newtonian because it's incorporating all these ideas. Now, your claim that by doing so, there's also a sort of metaphysical connection with ether theories. That's an interesting one.
Right the other way around. I don't say that you need this metaphysics in order to do this kind of mathematics, but it is historically clear that the idea of a plenum in which particles, whatever their nature is, exert on each other, direct a kind of mechanical interaction, is underlying the principle of virtual work as well as the minimization principle. Okay. That's all I say. Yeah, but I think it's quite interesting.
That is very interesting, indeed.
Yeah, I think I have to stop.
Okay.
I wanted to say something about the degravitazione, but
we will have a chance to talk. Yeah.
Yeah. Yeah, I'd like to make 2 points. The first one has just come up. It's about this Newton theory of resistance. He didn't for a moment think that that was necessarily the argument, the resistance that he would be arguing against with regard to Descartes' theory. It was just a possible theory of resistance which he started to develop. And we now know what it does apply to. It applies to hypersonic motion.
Yes, yeah.
Which is it is exactly correct for, or nearly exactly correct for. So he wasn't saying this is going to be the one about the Cartesian fluids, this particular thing.
No, I think it would actually have been, I think, so there's part of the argument which I think he probably would have been unsatisfied with, which is that he had to make the argument in a hypothetical form. If this is what you mean by a fluid, and if this is what you mean by a vortex, then this is the motion that will result. So that's why I said I think he's advancing the Cartesian program by giving the first sort of quantitative version of a vortex theory.
Well, the other thing I would like to say is that what it seems to me, in editions of Principia and other books on the subject of the book 2 of the Principia, people seem to have missed one particular aspect of section 9, and that is the corollaries to propositions 51 and 52, especially those to proposition 52. Now,
so 52 is the one dealing with a spherical body rotating with spherical shells.
The proposition is, but the corollaries could be about any vortex. And the corollaries seem to me to give an exact description of the 2 limiting cases of vortex motion, the free vortex and the fixed vortex, and show how one transitions into the other. And it seems to me that that's an exact description, which nobody has actually noticed that it's an exact description of that. And if you apply either of those cases or anything in between, you do not get Keplerian relationship between T and R. And I think people have missed that aspect of the Newtonian proposition because they point out propositions 51, 52 don't apply, they're not correct. But the corollaries don't apply to the propositions particularly, they're just about any vortex motion, and they are correct. And I think that's worth looking at in this context. And whatever Johann Bernoulli said, I think those are still correct by any modern standard.
So I'd be interested to talk with you further about this. I'm guilty as charged as well in terms of not having noticed this feature of the corollaries. So I think the question would be whether the criticism by Bernoulli and others, how that impacts the arguments in the
I
corollaries.
think they're
So-
criticising the Scholium to proposition 53, where he goes into
No,
various
that's certainly
elaborate
true, but
arguments. And most people would criticise that.
But there's a set of stability assumptions that are important throughout the entire section. So I think there's a delicate question of how.
But I think you're just talking about any vortex motion of any kind. Could be a free vortex, could be a fixed vortex. Those are complete limiting conditions for any vortex motion, regardless of stability or other conditions.
Okay, well, let's talk about this further.
Okay.
I don't